to the course on basic electronics. So we'll be discussing about module 2, that is BJT and FET. So BJT, its content goes like this. BJT, bipolar junction transistor, introduction, transistor construction, transistor operation, common base configuration, transistor amplifying action, common emitter configuration, common collector configuration, the limits of operation, operating point, fixed bias configuration, field effect transistor, introduction, construction and characteristics of JFET, transfer characteristics of depletion type MOSFET and enhancement type MOSFET. So coming to the bipolar junction transistor. So this bipolar junction transistor has 3 layers of semiconductor material. So this transistor was developed by Dr. Shockley along with Bell Laboratories team in 1951. The transistor is a main building block of all modern electronic systems. It's a three-terminal device whose output current, voltage, and power are controlled by its input current. In communication systems, it is the primary component in the amplifier. An amplifier is a circuit that is used to increase the strength of an AC signal. Basically, there are two types of transistors. One is bipolar junction transistor, field effect transistor. So this bipolar junction transistor has 3 layers of semiconductor material. These are arranged either in NPN, that is N-type, P-type and N-type sequence, or in PNP sequence, that is P-type, N-type and P-type sequence. And each of the 3 layers has a terminal. A small current at the central region terminal controls the much larger current, or we can say the total current that flows through the device. This means that the transistor can be used for current amplification. So it can also perform voltage amplification. Because the transistor has two PN junctions, its operation can be understood by applying PN junction theory. The currents that flow in a transistor are similar to those that flow across a single PN junction. And the transistor equivalent circuit is essentially two PN junction equivalent circuits. There are 3 sets of current voltage characteristics for defining the performance of a transistor. So coming to the BJT operation, a PNP and NPN transistors, a bipolar junction transistor is simply a sandwich of one type of semiconductor material, that is P-type or N-type, between 2 layers of the opposite type. A block representation of a layer of P-type material between 2 layers of N-type. It is shown in this figure. So this is described as an NPN transistor, and the other type of transistor is PNP transistor. So this will be consisting of a layer of N-type material between 2 layers of P-type material. So for reasons which will be understood later, the center layer is called the base. One of the outer layer is termed as collector, and the other outer layer is referred to as the emitter. The emitter, base and collector are provided with terminals which are appropriately labeled as E, B and C. So the two PN junctions exist in each transistor. The collector base junction and the other one is emitter base junction. Each of these junctions has the characteristics. So the circuit symbols for PNP and NPN transistors transistors are shown here. The arrowhead on each symbol identifies the transistor emitter terminal and indicates the conventional direction of current flow. For an NPN transistor, the arrowhead points from the P-type base to the N-type emitter. For a PNP device, the arrowhead points from the P-type emitter to the N-type base. Thus, the arrowhead always points from P to N. So, the two transistor packages for a low power transistor and a high power device. So, low power transistors generally pass currents of around 1 milliamperes to 20 milliamperes. Current levels for high power transistors range from 100 milliamperes to several amperes. The high power transistor is designed for mechanical connection to a heat sink in order to prevent the device from overheating. Semiconductor device packages can also be discussed. So coming to the NPN transistor operation. So here this diagram illustrates the depletion regions and barrier voltages at the junctions of an unbiased NPN transistor. So these were explained in the earlier modules also, like in semiconductor materials. Although it's not shown in the illustration, but the center layer of the transistor is very much narrower than the two outer layers. The outer layers are also much more heavily doped than the center layer, so that the depletion regions penetrate deep into the base. So because of this penetration, the distance between the two depletion regions is very short. Noting that the junction barrier voltages are positive on the emitter and collector and negative on the base of the NPN device. So considering this diagram, it shows an NPN transistor with external bias voltages for normal operation. The base emitter junction is forward biased and the collector base junction is reverse biased. So considering the polarities of the external bias voltages, the forward bias at the base emitter junction reduces the barrier voltage and it causes electrons to flow from the N-type emitter to the P-type base. The electrons are emitted into the base region, hence the name emitter. Holes also flow from the P-type base to the N-type emitter, but because the base is much more lightly doped than the collector, almost all of the current flowing across the base emitter junction consists of electrons entering the base from the emitter. Thus, electrons are the majority charge carriers in an NPN device. The reverse bias at the collector base junction causes the collector base depletion region that penetrates deeper into the base than when the junction is unbiased. The electrons crossing from the emitter to the base arrive quite close to the large negative positive electric field at the collector base depletion region. Because electrons have a negative charge, they are drawn across the collector base junction. By this bias voltage, they are said to be collected. Some of the charge carriers entering the base from the emitter do not reach the collector but flow out through the base connection. So this can be seen here, but the path from the base emitter junction to the collector base junction depletion region is much shorter than that to the base terminal. So only a very small percentage of the total charge carriers flow out of the base terminal, and because the base region is very lightly doped, there are few holes in the base to recombine with electrons from the emitter. The result is that about 98% of the charge carriers from the emitter are drawn across the collector base junction to flow through the collector terminal and the voltage sources back to the emitter. Another way of looking at the effect of reverse biased collector base junction is from the point of view of minority and majority charge carriers. It has already been discussed that a reverse biased junction opposes the flow of majority charge carriers and assists the flow of minority carriers. Majority carriers are, of course, holes from the p side of a junction and electrons from the n side. Minority carriers are holes from the n side and electrons from the p side. So, in the case of an NPN transistor, the charge carriers arriving at the collector base junction are electrons traveling through the p type base. Consequently, to the collector base junction, they appear as minority charge carriers, and the reverse bias helps them to cross the junction. Because the base emitter junction is forward biased, Because the base emitter junction is forward biased, it has the characteristics of a forward biased diode. Substantial current will not flow until the forward bias is about 0.7 volts. That is for a silicon device, or about 0.3 volts for germanium. Reducing the level of the base emitter bias voltage reduces the PN junction forward bias and thus reduces the current that flows from the emitter through the base region to the collector. Increasing the base emitter bias voltage increases this current. Decreasing the base emitter bias voltage to zero or reversing it cuts the current off completely. Thus, variation of the small forward bias voltage on the base emitter junction controls the emitter and collector currents. And the base emitter controlling voltage source has to supply only the small base current. So, considering the PNP transistor operation, in an unbiased PNP transistor, the barrier voltages are positive on the base and negative on the emitter and collector. As in the case of the NPN device, the collector and emitter are heavily doped so that the base emitter and collector base depletion regions penetrate deep into the lightly doped base. A PNP transistor behaves exactly like an NPN device, with the exception that the majority charge carriers are holes. The base emitter junction is forward biased by an external voltage source, and the collector base junction is reverse biased. Holes are emitted from the P type emitter across the forward biased base emitter junction into the base. In the lightly doped N-type base, the holes find few electrons to absorb. Some of the holes flow out via the base terminal, but most are drawn across to the collector by the positive negative electric field at the reverse biased collector base junction. Variation of the forward bias voltage at the base emitter junction controls the small base current and the much larger collector and emitter currents. Considering the bipolar devices, although one type of charge carrier is in the majority in a PNP or NPN transistor, two types of charge carriers, that is holes and electrons, are involved in the current flow. Consequently, these devices are termed as bipolar junction transistors. So, this is to distinguish them from field effect transistors that are termed as unipolar devices because they use only one type of charge carrier. So coming to some of the BJT voltages and currents, the terminal voltage polarities for an NPN transistor as well as the conventional current direction. The direction of the arrowhead indicates the transistor bias polarities. For an NPN transistor, the base is biased positive with respect to the emitter and the arrowhead points from the base to the negative emitter. The collector is then biased to a higher positive voltage than the base. Figure shows that the voltage sources are usually connected to the transistor via resistors. So the base bias voltage is connected via resistor RB and the collector supply is connected via RC. The negative terminals of the two voltage sources are connected at the transistor emitter terminal, that is VCC, is always much larger than VB, and this ensures that the collector base junction remains reverse biased, positive on the collector and negative on the base. Typical transistor base emitter voltages are similar to diode forward voltages, 0.7 volts for silicon transistor and 0.3 volts for a germanium device. Collector voltages might be anything from 3 volts to 20 volts for most types of transistors. For a PNP device, the base is biased negative with respect to the emitter. The arrowhead points from the emitter to the base, and the collector is made more negative than the base. Figure B shows that the voltage source is connected via resistors and the source positive terminals connected at the emitter with VCC that is larger than VB. So the collector is more negative than the base, and thus collector base junction is kept reverse biased. So all BJTs, maybe NPN or PNP, are normally operated with the collector base junction reverse biased and the base emitter junction forward biased. In the case of a switching transistor, the collector base junction may become forward biased by approximately 0.5 volts. Also, in transistor switching circuits, the base emitter junction can become reverse biased. And considering the transistor currents, the various current components that flow within a transistor. So the current flowing into the emitter terminal is referred to as emitter current and is identified as IE. And for PNP device, IE can be thought of as a flow of holes from the emitter to the base. So this indicates IE direction is the conventional current direction from positive to negative. Base current IB and collector current IC are also shown as conventional current direction. Both IC and IB flow out of the transistor while IE flows into the transistor. Therefore, as discussed, almost all of IE crosses to the collector and only a small portion flows out of the base terminal. So 96% to 99.5% of IE flows across the collector base junction to become the collector current. That is IC is equal to alpha DC IE. Here alpha DC is the emitter to collector current gain, or it is denoted as ratio of collector current to emitter current. So from equation alpha DC is equal to IC by IE. Numerically alpha DC will be around 0.96 to 0.995. So the collector current is almost equal to the emitter current, and in many circuits IC is assumed to be equal to IE. So for reasons that will be explained later, alpha DC is termed the common based DC current gain. Because the collector base junction is reverse biased, a very small reverse saturation current flows across the junction. ICBO is named the collector to base leakage current, and it is normally so small that it can be ignored. So substituting for the emitter current as IC is equal to alpha DC IC plus IB. Here beta DC and beta DC is the base to collector current gain, and alpha is the alpha DC is the emitter to collector current gain. And coming to the different operating conditions for a transistor, the different operating conditions for transistors are like one is saturation region, active region, the other one is cutoff region. So condition when forward, reverse, and emitter base junction is forward biased and the collector base junction is reverse biased, it is said to be, the transistor is said to be in active region, its region of operation. When emitter base junction is forward biased and collector base junction, both the junctions are forward biased, it's said to be operated in saturation region. When both the junctions are reverse biased, it's said to be operated in cutoff. When emitter base junction is reverse biased and the collector base junction is forward biased, it's said to be operated in the inverted region.